Test 4. These were tough problems. These were a kick in the head. Number 2. A bubble starting at the bottom of a soda bottle experiences a constant acceleration A as it rises to the top. Haven't they ever heard of viscosity? It would travel at a constant speed. Anyway, takes time t. How much farther does it travel in the last second of the journey than in the first second? Yikes. There's the equation. There's the part we care about. There's the path of the bubble. This is how far it goes in the first second. This is how far it goes in the last second. So we have 1, 2, 3, 4 distances to care about. There's the first 2. Starts at 0. 1/2 a1 squared. There's the second 2 distances we worry about. There's a little bit of subtraction. That's how far you go in the first second. There's a little bit of rearranging and then a little bit of subtraction. And then we have to find out how much farther it goes in the last second than the first second. So that gives us this. The equation's not so bad until you use it 8 times. Number 12, the figure above shows a uniform bar of mass m resting on 2 supports. A block of mass 1/2 m is placed on the bar twice as far. Okay, I'll write that down. Twice as far from support 2 as support 1. If F1 and F2, okay, I'm confused already, so let's just talk about F1 and F2. If the bar is pushing on the supports are pushing on the bar, and then we've got these 2 different masses, and already I can see that F1 plus F2, the upward forces equal the downward forces, so we're good. But what are we looking for? We're looking for the value of the ratio F2 to F1, and that means we're going to have to go to rotation. I'll take the left-hand side as the rotation point, and tau equals F perpendicular times R, so that means we have 1/2 mg times a distance x, and then we have the weight of the bar is 3/2 x. Notice if the total bar is 3x long, then that's halfway to the center of the mass of the bar. And then we have F2, and then we can solve for F2, and that's exciting because we have this other equation, and then we can solve for F1, and that's exciting. And then the ratio of F2 to F1 involves fractions. You like fractions, don't you? So again, here we have a 2-step problem. If that bar is balancing, then the forces balance and the torques balance too. Number 21, a particle of mass 1 kilogram is acted upon by a variable force whose strength is given by the graph below. Above, below. If the particle's speed is 0, what's the speed after 4 meters? Work is equal to the integral of FDR. Work is equal to the area under this force versus distance graph. 1/2 base times height is 10. Length times width is 20. 1/2 base times height is 20. 10 plus 20 plus 20 is 50 is equal to 1/2 mv squared, and that means mass is 1 and velocity is 10 meters per second. Number 22, the radius of a collapsing spinning star, assumed to be a uniform sphere, decreases to 1/16 its initial value. What is the ratio of the final rotational kinetic energy to the initial rotational kinetic energy? Well, we've got 3 things going on here. Moment of inertia proportional to radius squared. That's the equation for a uniform sphere, but yeah, proportional to radius squared. Angular momentum, I omega. This stays the same because there's no external torque on the system. Rotational kinetic energy, I omega squared. So let's work through this. The new moment of inertia is smaller by 16 squared. That means that the omega is bigger by a factor of 16 squared, and both play a role in rotational kinetic energy. I makes you smaller, omega makes you bigger, but it's omega squared which makes you bigger more than you get smaller. C is the answer. Work through it yourself. I got one more to do. 31. The rod shown above can pivot about point. I didn't include the rod here. X equals 0 and rotates in a plane perpendicular to the plane. Its linear density, lambda, increases with x such that lambda of x is equal to kx, where k is a positive constant. Determine the rod's moment of inertia in terms of its length, L, and total mass, M. Totally skip this question if you get a question like this on a multiple choice. And when I say skip, just take a guess there. It's a multiple. We'll do it in a second, but I have a feeling that there'll be a question like this on the open response, the free response part of the test this year. And I have that feeling because I like these types of questions. That's why I don't bet on things, because my feelings usually aren't right. But here we have lambda that's linear density, mass per length, but it changes. So dm dx is equal to kx as given in the problem. That means dm is equal to kx dx. Let us integrate that from 0 to L. We'll get a total mass of 1/2 KL squared, an answer to the question nobody asked. We don't care about that. We want moment of inertia, but somebody might care about this later. So hold on to it and get moment of inertia. Integral of r squared dm. Bing. Bang. Boom. All right, I believe you because I don't really care. But wait a minute. We have mass. We have I. We're looking for which one of these i's works, which one of these moments of inertia is correct. We solve for k. Can you do it? Can you do it? You can do it. Yeah, we can do it. I probably couldn't have done it in less than 80 seconds or less than 77 seconds, which is what you got per question on a standard multiple choice test. But that, after all, is why there's editing.